the OpenFold Collab demo. You heard from Mohammed yesterday about the OpenFold project. One of the first projects being to reproduce AlphaFold 2 for structure prediction, protein structure prediction. So there's a couple of different things you can do with the OpenFold codebase, and I'm going to show you how to run inference on make a structure prediction of a single protein. We also have support a couple other modes of prediction, including multimer prediction and single sequence prediction, but this is sort of the base AlphaFold style prediction. All right, so this is a Collab notebook. It will handle the installation of the environment inside of the Collab notebook. So you start off by giving it a sequence. This is the sequence for MCL1. You'll see this protein used in the demos that follow today. But you can put in any sequence here. If you want to put in a multiple sequence, you would have to format it with a colon between the sequences. And here you can choose whichever weight set you want. So you can either use the OpenFold weight sets, which are the ones that were trained by us, like retrained, that are different. Or you can use the original AlphaFold rates here. You can also choose your model mode, either the monomer or the multimer mode. If you use the multimer mode, we don't have OpenFold weights for the multimer mode yet. And you can also choose whether or not to relax your prediction. All right, so I mentioned that it handles the installation steps, it downloads the weights, it does the Python imports, and then you start with the process of making a prediction. So for the original AlphaFold model, the first step to making a prediction is to have the MSAs, the multiple sequence alignments. So that's what's done in this cell. I'll show you under the hood here. This cell actually runs sequence alignments against a number of data sets, but this is actually smaller than the full set of data sets that are available or that are used for training the full model. This is because this is mostly for a demonstration purpose. If you really wanted to, you can actually change some of these values to be smaller or to be bigger, I guess. But if you change them to be smaller, it means that the MSA will take less time, but this comes at the cost of the quality of the predictions, as you might expect. The sequence alignment will be less deep, and there will be sort of a less rich feature set. Yeah, but if you do that, it sort of means that the predictions can run faster, and it's sort of, I've used it a number of times as a way to help debug and help make sure that the full model runs. Okay, so when you run the sequence alignments, you get a plot that looks like this. This shows you roughly the number of matches you're getting for each residue position in this sequence alignment. And then after that, you have the prediction. So what happens is that it takes the MSA, converts them into features for the model, and then it runs a forward pass of the model to make an initial prediction. And then in our case, it also runs, in this case, I also asked it to run Amber relaxation. So it's using OpenMM under the hood to run relaxation. And so you get a structure that looks something like this. The coloring here indicates the model's self-confidence or predicted self-confidence in the accuracy of the structure. So what I mean by this is that the model has, when it's being trained, has an extra head where it's trying to predict the loss functions. It's two different losses. In this case, it's actually a number of losses, but here it's just showing you the LDT loss, which is the local distance loss, test loss. So here dark blue indicates that it's very confident in its predictions, which perhaps unsurprisingly is corresponding to these really rigid alpha helices, and then the light blue indicates regions of less confidence. You can also see this in another format, in like this more graphical format. So here it's the residues on the x-axis, the predicted LDT loss on the y-axis, and you can see sort of the regions that were earlier having less confidence. This predicted aligned error is another way of looking at this loss. This has to do with the alignment or the positions between any two pairs of residues in the predicted structure. And here the green, darker green indicates that it's more confident, it's higher accuracy prediction. Yeah, so I invite you to take a look at the notebook and insert your own favorite protein sequences and try to run it. I guess I'll note that this demo is good for visualization purposes, so it's like good for quickly visualizing this predicted structure and seeing the performance. All the prediction outputs are actually downloaded upon the notebook finishing. So then all the cells have run, the predictions are downloaded. If you want to run a lot of predictions, I actually recommend using the Python script to run it instead. So here's the OpenFold documentation, just fresh off the presses. And so, right, yeah, so basically you would end up using a Python script that looks something like this. You would have to download the databases yourself first in order to make the predictions, or else come up with sequence alignments from another source. But this would be better for the purposes of running a lot of predictions, or one of the requirements of running the Collab demo is also that you need to have a GPU instance of Collab. So depending on your account, depending on your settings, it could be more flexible to use the Python script version. Yeah, so that's what I mentioned, that this is sort of one demo that you can do with OpenFold. This is OpenFold inference. I mentioned that we also have solo-seq inference, which is the MSA-free prediction mode, multimer inference, which basically is based on AlphaFold multimer and uses the AlphaFold multimer weights to make predictions. It's also possible to do training. This requires a little bit more setup with the databases, which are available in our Rota bucket and on AWS. So those can be downloaded and formatted to train your own versions of OpenFold. It's also possible to do fine-tuning with OpenFold, which there are some documentations for that. Yeah, so with that, here's a couple of links to the GitHub and the Collab demo, and I'm happy to take any questions. Sorry, the question is, what happens if you run it for a protein complex? Protein RNA, we don't support that at this time. Yeah, that would be handled by models like RFAA or AlphaFold 3, but it's not supported at this time by this particular model.
Hi. So comparatively, how large are the databases in terms of straight like file size? Because running AlphaFold locally, the file sizes are on the order of terabytes. Yeah. And how much accuracy do you lose in the estimates by having potentially smaller databases?
I haven't personally done extensive benchmarking on the different data set sizes. I think it depends on the protein a bit, right? Like the target. If you've got a target that is perhaps already really well characterized by even a small set of any of your databases, then perhaps you don't need such a large database. You can do it with a small fraction of the database. But if you've got a protein that perhaps doesn't have as much representation, then perhaps you do need to use the full database. But yes, unfortunately, the databases are pretty large, like several hundred gigabytes large.
Any more questions for Jennifer? Perfect.
And if you run this locally, what hardware resources do you recommend? I mean, what type of GPU?
I think just a pretty, like you don't need any sort of special GPU for inference. For training, you would need a larger GPU instance, but or like more GPUs. But for this one, just running it on a single GPU is enough.
Okay, let's give her a round of applause. Thank you, Jennifer. Up next, we have Jeff Wagner from Open Force Field.
keyboard setup assistant. Okay. Yeah, so I'm Jeff Wagner. I'm the technical lead for OpenFold, and today I'm going to be running my first live demo since the RDK UGM disaster of 2022. So I've got this notebook. I'll go ahead. It's available on Collab, but I didn't drop it in the Discord yet. I'll drop it in right after this talk so you can go in and play around. But right now I'm running this locally. So going to start with a bunch of imports. There's a lot of gobbledygook. Don't worry about this. And in fact, let me run this live. Let's do this live. Restart kernel, clear outputs of all cells. So, I'm talking between OpenFold and OpenFree Energy. And what I want to do is give you basically the pathway from going from an OpenFold prediction to the beginning of an OpenFree Energy protein ligand simulation. So the OpenFold prediction, Jennifer sent this over the other day. It's got hydrogens added. They did a relaxation in amber, and so there's a PDB file of it. And what I'm going to do here is I'm going to take that PDB file, going to superpose a ligand on top of it, show you how to solvate the entire complex, assign parameters, and then simulate it. The first thing we do is that we load the topology from PDB. This is a OpenFold topology call. And the OpenFold topology.from PDB method recognizes proteins made of all the 20 canonical amino acids in various protonation states. It recognizes waters and sodium, common salts. But if you have anything else, for example, in this one we have a ligand, that ligand needs to have full connect records, and we need to provide the full chemistry for that as well. We provide that using the OpenFF molecule object, and here we're just making a molecule from smiles. So we've loaded this in, and anytime I show you a protein visualization today and I don't zoom it in, just yell at me, say make it big. But okay, yeah, we've got the OpenFold prediction here, and we've got this small molecule ligand. Whoops. And now we have used the OpenMM PDB fixer tool. So this complex doesn't have waters yet, and we don't really recommend using implicit water. We're co-optimized with TIP3P at OpenFold, and so here I've just dumped out the topology to a file. I called OpenMM's PDB fixer to load it up, add some water, dump it back out to a PDB, and then we've loaded it back into the OpenFold toolkit. So, I shouldn't have run those both at the same time. Okay, there we go, and then I'll get this next one going. Okay, so, imaging aside, because imaging is a pain, we've got a periodic box now, because we've got a big water box. But this is that same complex, same ligand, with a number of sodium and chloride ions in the solvent now, and a ton of water around it. We can zoom in, yeah, so you've still got the ligand here up in the pocket. So what we want to do next is assign physics parameters to this complex. And we're going to do that by making an OpenFF force field object. That OpenFF force field object is made of the SAGE 2.2 force field, as well as our port of the Amber FF14SB force field into OpenFold format. Let's take a minute to talk about what our force fields look like. So, oh, I didn't get the aspect ratio right. Well, so I'll have to scroll around a little bit on this. Each parameter in our force field, for example, here we're looking at the chemical pattern for a bond parameter. We know that it's a bond parameter because it tags two atoms. This :1 and this :2 indicate that we've tagged two atoms in this pattern, and the atoms in particular that we've tagged are required to be a carbon with 4 bonds, so element number 6, X4, and a nitrogen with 3 bonds, and we're referring to the bond between these two, and we've explicitly said that must be a single bond. We've also said that this pattern should only match in the context of being neighbors to an sp3 carbon, so a carbon with 3 bonds, that's double bonded to an oxygen with only 1 bond and no formal charge. If we look at the Kekulé structure of 2 molecules up here, we've highlighted the atoms that match each query in the corresponding color. Oh good, and the colors aren't too washed out. And any place where this pattern fully matches and the green bond parameter would be assigned, we've highlighted it in green. So we've got 2 molecules shown here. Now, what do actual OpenFF force fields look like? So this has been the chemical pattern to match a bond. But what does the, where do the physics parameters come from? So let's go ahead, and I've actually got OpenFF 220 right here. Might be a little small, sorry about that. But you see that, for example, if we go up to the bond section, we've just got a big list of parameters. And these are substructure queries that you do want to calculate structure of a molecule. We start from very generic parameters. So this is just like any sp3 carbon bound to any other sp3 carbon. And then further down in the list, we have more specific parameters, like an sp3 carbon bound to another sp3 carbon with an electron withdrawing group or something, and maybe that'll tighten the bond because there's a little electron deficiency or something. Don't ask me, it's not like I have a PhD in chemistry. Anyway, with each of these, we have physics parameters associated. So we say, here's the length and the K. For those who aren't familiar with molecular mechanics, we treat these like little springs with a natural length and a relaxation constant, or a spring constant. And then as we go further down in the force field, we have more sections. So we have angles. These define like the equilibrium angle involving 3 atoms. We have torsions involving 4 atoms, and they have kind of a funky functional form. So there's just like a ton of gobbledygook here. They're not the best examples. But this is fundamentally the sage force field. Everything that people have been talking about the last few days with like, oh man, we spent 1 billion GPU hours on free calculations. At the root of it, our latest and greatest force field is this file, and here's the file of it. So let's head back. The other thing I want to note is, like I said, there's that very generic sp3 carbon parameter at the top of the list of bonds, and then further down there's other parameters that might override it. And that lets us easily extend our force field. So if there's some deficiency, we can just say, oh, well, we'll add a more specific parameter at the bottom to, in this specific situation, assign a different number of physics values, or different physics values. When we have a protein ligand system, we basically append all of the protein parameters to the small molecule force field. So it'll assign to anything that's not a protein, it gets these first parameters from the small molecule force field. But then in each one of those sections, so in the bond section of this joint force field, it's going to have all the SH parameters and then all these protein-specific parameters that only match if it's a whole amino acid. So basically, in this topology, all the waters are going to get SH parameters, the ions are going to get SH parameters, the small molecule is going to get SH parameters, and the protein is going to end up getting amber FF14 SV parameters. Oops, let's get this out of here. All right, so we've gone ahead, we've made a force field, and then we've said, go ahead and do searches, like I'm showing down here, do searches over all the molecules in the system, assign them all the parameters. If there's a small molecule in there that we don't have library charges for, so if you use a protein force field, you know that it just knows the charges that should be on all the amino acids and it just slaps them on. But for small molecules, there's more small molecules than you can usefully list to pre-compute charges. So we, on the fly, call out to RDKit and Amber tools to generate a conformer, do an AM1 optimization, and then pull out partial charges from that. All that magic happens in this one line right here. The create interchange line. So after this, we have a representation of this whole system with parameters applied, and then we go into OpenMM land. We make an integrator that describes the temperature that we want the simulation run at, the coupling frequency to the thermostat, and the time step that we want to take, in this case 2 femtoseconds per time step. We take our interchange and send it to an OpenMM simulation. We use some OpenMM specific wording to say we want a trajectory out from this so we can see what happened, and then we ran 1,000 steps of simulation.
Thanks, Jeff. You got about 25 more minutes.
Oh, do I?
Yeah, yeah.
Okay. Okay, well, so you know everything you need for the OpenFE demo then. I guess I'll just talk about some OpenFF stuff. here we see very good agreement in all these energy components. I think the non-bonded stuff gets weird. Different engines do different optimizations. They have different rules and words, but generally we're just going to roll this in. 1e negative 4 relative there.
Very cool, Jeff. Naggle and interchange. It's very cool. Do you have more?
Through a USB port, and it's done.
Okay.
But I can help you.
You already know kind of everything you need to know for these products too, and everything you need to know for the OpenFE demo. But yeah, I think I've got more. Let me go ahead and stop this. This is messing with my screen. So, I have a story to tell. And the story is, Jennifer sent me the OpenFE, the OpenFold prediction. And Earthman said, oh, that's great. We have some MCL1 ligands, and we can go ahead and put that through OpenFE. We've got the ligands, we know the relative energies, so we can try to predict them. And I was too lazy to go and look at the actual ligands. Instead, I just went to the protein data bank. I took this, and I searched for MCL1 with ligand. And I pulled out this PDB, 4HW3. And 4HW3 has this big old ligand in it. It's got a scaffold. It's going to be rough because it's a live demo. But it's got this kind of sulfur-containing scaffold up here with the carboxylate group. That's exactly what I just showed you in the demo. But 4HW3 also has this ligand reaching down into the pocket. But OpenFold predicts there is no pocket. And I thought, boy, wouldn't it be interesting if we could use, this thing where we could rapidly iterate on loop ligands and get physics parameters for them using Naggle. And we can save some more time by using interchange component combinations that have to go painstakingly reparameterize a big protein every time with this protein force field from an atom type blend that really doesn't want to be in Smirnoff land. And yeah, maybe we could do something where we start with the ligand that we already had, and we say, hey, just start growing into that pocket. Literally just add one methyl at a time in that direction until this pocket opens up. Because if I were a net chemist and I had some intuition, I knew that the scaffold bound, and I was like, oh man, I think I could dig in there, but the protein structure won't let me. Can I use real physics? Can I use real molecular probes to grow in that direction and force open this pocket that I suspect exists? So again, here I'm showing the OpenFold prediction with the surface, and so the surface shows that this deeper part of the pocket is closed. Whereas if I go on the PDB and I find a different ligand, or a different experimental structure with a big ligand in it, there's this pocket down here that would otherwise be inaccessible. So here's the cycle I have in mind. I want to take the protein ligand complex and relax it. In case there's any clashes, I want those to be resolved so that we've got a protein ligand complex, and if there's any opportunities to grow into that pocket, I want them to be cleared, not have steric clashes. Then, from that, I want to take the small molecule, and I want to propose mutations to that small molecule. And so these would be chemical reactions, like adding a methyl, adding a nitrogen, replacing a hydrogen with a heavy atom. And for each one of those mutation candidates, I want to go for cheap pre-screen and say, hey, are any of you going into the pocket, or are you all just So we want to make this cycle of, start with that initial scaffold and just start growing down in the pocket. And let's see with some of the new stuff that's coming out, with nagging, with interchange, if we can just quickly make a loop that does this. All right, so I'm going to reload that initial topology, so this is exactly the same as what I was showing you before. Though I do want to point one thing out, and I'll get the next part running just in case it takes a little while. Okay, so I'm going to pull in that complex that I showed you before, and I want to point one thing out about this. This is the exact same things we've used earlier on, but even this starting ligand didn't totally fit inside of the OpenFold prediction. And this is kind of a ligand post that I found in a dumpster. This is no fault of anyone's, I'm just putting an incompatible ligand in with the protein. So this would be a good test. So if I can do this relaxation of a ligand candidate in the binding pocket, I should be able to resolve some of these clashes where this ligand is clipping through the protein surface. So define some boilerplate so that I don't have to write so much code later. And let's get my chef's tools ready for this clip and show. So I'm going to be using 3 force tools. I'm going to be using Sage. I'm going to be using FF14SD, both of these you've seen twice before. But then also, because, I'm doing this stupid thing where I'm just throwing atoms at other atoms, I'm going to wind up with steric clashes. And I don't want those to dominate the energy function as I'm calculating these interaction energies for molecules that are getting thrust into this pocket. And so I want to be a little bit more relaxed about steric clashes. Like, I don't want there to be nuclear fusion, but I'm doing things that are fundamentally incompatible with each other's geometries, so I'm going to relax it a bit. And I thought about a bunch of different ways to do this. I could go and say, well, I've got this combined interchange. Some of the atoms are in the ligand, some of the atoms are in the protein. Can I go find all the ligand atoms and just reduce their van der Waals, but then it would be really complicated. And I realized that because of the way that our force fields are just Python objects, one way I could make the ligand van der Waals parameters a lot more forgiving is just loop over all the van der Waals parameters and say, you're half of what you used to be. The end. So now I've got this modified version of Sage 2.2, where it's very forgiving to van der Waals clashes. I also want to point out that we have this tortured Smirnov format protein force field that it's tortured because it's ported in from an atom type land. And so it's got bajillion parameters to make sure that it matches. And to actually apply this to a protein takes 22 seconds. Our protein force field rosemary is going to be way faster than this. This is just because there's like a bunch of translation done from bringing a protein force field from atom type land into Smirnov land. And I'm also, for performance reasons, I'm going to create a protein simulation ahead of time as well. So here's the business logic of that first part of the cycle. We've got a ligand in a binding pocket. We want to do an energy minimization and a short molecular dynamic simulation to let any clashes be resolved. So this takes in a protein interchange. That's a thing that was expensive to make, so we're keeping one around and we're just going to update its position so we're not going to remake it. I'm taking a ligand as an open force field molecule and a force field fill ligand. This is going to be that softened force field. Or no, this is going to be a real force field, sorry. So, to save time, instead of using AM1BCC through anti-chamber to charge this ligand, we're going to use NAGL. This is going to take a few milliseconds. That's instead of like 30 seconds. So that's a big win. When we assemble this complex, this protein ligand complex, we're not going to reparameterize the whole thing every time. We're going to take that one protein interchange that we made and use interchange.combine to combine it with this new ligand. And what's cool is that we need to do this custom stuff in OpenFold. So in my early prototypes of this, I'd say, hey, ligands, try to go get in conflict with the protein and then minimize their energy. And of course, what would happen is the ligand would just push itself out of the binding pocket and out of the solvent. And then I said, oh, well, the ligand scaffold can't move. And then the ligand would start pushing the entire protein out of the way. So both of these were bad. And I can go just under the hood. So this whole thing so far has been in nice abstract OpenFF land. We're using interchanges, but we need to do something really specific. We need to go into the resulting OpenFF simulation and restrain some out of gobbledygook to say, go ahead, minimize this simulation, and then update the interchange with the new coordinates that came out. So now we'll have a complex that no longer has hysteric flashes. It's relaxed, it's resolved. This thing hates me. So I had shown you that earlier thing where I said, oh, well, the scaffold is in conflict with the OpenFold prediction. And so to test out this method I just defined, I'll go ahead and run it on the scaffold, and let's see if it has those steric flashes that I had shown you earlier. No, it doesn't really. So this is great, and this whole thing ran in 7 seconds. So for 7 seconds per mutation candidate, we can take an entirely new small molecule and go ahead and resolve it and get any protein flashes out of it. This includes going into OpenIM, running 1,000 steps of molecular dynamics after organization. Cool. 7 seconds per run. So the first part of the cycle is complete. Now, we don't have any native tooling to propose chemical mutations to a ligand. If you try to change the chemistry of an open force field molecule, you'll almost certainly get an error unless you really know what you're doing. But you know what is really gung-ho about letting you change molecules? Is RDKit. And we use RDKit for a lot of stuff on our backend, and so we expose our RDKit interoperability layer to users whenever they want it. So here, this is a method that just mutates the ligand. It takes an open force field molecule as a ligand. It sends it to RDKit, and then it says, hey, RDKit, use all your nice reaction mechanisms to propose mutations to this ligand. And these are SMERX reactions. One of them says, take a pattern that matches any atom bound to any terminal atom. So the terminal atom could be hydrogen, it could be chlorine, any atom bound to any terminal atom, and try mutating that terminal atom into a methyl. So basically start growing. And the other two mutations are take any carbon-hydrogen bond and try changing the hydrogen into a nitrogen, or try changing the hydrogen into an oxygen. So these are all things that are going to increase the size of the ligand. And we say, okay, RDKit, you're great at this, go ahead, run these reactions on the input. So gobbledygook to get the RDKit, like the new molecule sanitized, and if it has any new stereocenters, those have to be signed. So gobbledygook, and then a quick thing to let us view the output. And here's the output of this mutation process. We've got the core scaffold, and it's going to be confusing because the core scaffold likes to flip upside down. So watch the sulfur. But it's taking the core scaffold, and it's tried adding a methyl here, it's tried adding a methyl here, and note that that's different because the sulfur's flipped. It's tried adding methyls in 6 places, corresponding to the reaction that we requested. It's tried adding nitrogens in 2 places, 3 places, and it's tried adding oxygens in 3 places. Alright, cool. So, step 2 of the cycle, done. We've got a method, it needs an open force field molecule, spits out a bunch of new open force field molecules that have mutations. Now, because it's going to take 7 seconds per evaluation to say, hey, how's the interaction energy between these 2 things? Or not 7, but it takes 2. We're going to do a quick screen and say, let's only keep the mutations of that core scaffold that are going to move us deeper into the pocket. This one's not bad. I just say, take a molecule, a proposed mutation, calculate its unweighted center of mass, and then see if it gets closer to this arbitrary point in the pocket. Okay, so here's all the candidates that were predicted, and then this number at the end is the distance between their center of mass and that point in the pocket that I want the ligand to grow towards. Done. And finally, we want to pick the candidate among those with the most favorable interaction energy. This is going to use that soft force field, where we've reduced the intervals radii. So let me get this running. And the way that this works is, it's a little bit janky, it's just going to work in vacuum, but it's going to say, well, the interaction energy between the protein and the ligand is the total potential energy of the protein-ligand complex in vacuum, minus the energy of the protein by itself in vacuum, minus the energy of the ligand by itself in vacuum. And so as we go through the implementation of this, it's going to take in that protein interchange. We've is I'm lazy and I runs in a few milliseconds, so we'll just use it again. We're going to calculate the ligand energy using something similar to that table that I showed you before, comparing all the energies. We just say, OpenMM, here's the ligand, what's the total energy vacuum at the end? And finally, we're going to reuse this protein interchange to combine with the new ligand interchange, and this way we're saving 22 seconds a pop. And we can quickly evaluate the OpenMM energy. Alright, so here's the loop where I've implemented this cycle. This loop's going to run 15 times, and we'll see if I decide to let it actually finish. And yeah, so here it's proposing mutations. It's deciding which ones are actually close to the target point. So right now I have a program to just keep the top 3 candidates that are moving center fast in the correct direction. And then for those top 3 candidates, it's evaluating the interaction energy between the protein and the ligand. And in the first few rounds, there's room to grow. The protein hasn't started encountering any steric clashes, so these energies are fairly negative. It's like, hey, yeah, the ligand wants to be here. You can add a methyl, you got on your own. But as we go further, we start seeing steric clashes, right? We've got one candidate at negative 202 kilojoules per mole, one at negative 158, negative's good, that means they want to be together. And then we have one candidate at 98,000. So we're starting to encounter steric clashes, and that's why it's important to have this minimization step. And it's going through rounds, and as we get to these further rounds, so here we're into round 4, it's getting steric clashes in most steps, so it's still finding candidates that are good additions. And do I want to let this finish? I don't think I want to let this finish. I'll jump to the end. So here is what this trajectory of scaffold growth has looked like. Will it blend? Yes. Oh, no. It partially blended. Live demos. In fact, I might not even be prepared for this. Did we get all 14? No. Okay. Well, I think I can show it better in the later slide, or in the later section. But yeah, sure enough, so we have the initial ligand, and at least for the first few steps, we can see it growing. You all should yell at me, make this big. This is your fault. So in these initial steps, we see it growing from the scaffold. It's picking the correct direction. Sometimes it picks a nitrogen instead of a carbon to improve interaction energy. And it's generally growing in the direction that we want. Yeah, okay, so this is as far as we get here. But yeah, it's sometimes going wide, it's sometimes going deep. But the loop is working, and it's running one loop about every 10 seconds. The question is, did we get the right pocket? And so here, I'm superposing the original ligand, the one that initially set off this whole investigation when I found a crystal structure that had a big ligand that was going very deep into this pocket. And again, I'll show you a little bit this big. But yes, it turns out that just by naively having the suspicion that there's a pocket over there and telling the ligands to grow in that direction and iteratively
Any questions?
Nice demo. One question is, interchange, up farther, it looked like you were saying it's still a beta version. Is it a beta version or is there a release version of interchange? Meaning, is it safe?
So the way that you'll know, so interchange as a whole package is production ready. There's some functionality that's new. So and you'll know when you're using it because it will yell at you if you don't set that environment ready.
How about if I'm doing 10,000 ligands?
10,000 ligands in this loop?
Yeah. Like, I'm not going to look at, it's like I'm asking, is it safe, you know, and what I'm hearing is that it may not be safe.
The two things that we don't endorse right now are the complete stability of interchange.combine. We're validating that just by putting a ton of stuff through it and seeing
Right.
what happens. And NAGL. So these are both things that we expect to become more stable in the next year. NAGL will have a full release, and I think interchange.combine is likely to be removed from behind the experimental wall. And so, yeah, I think in the next year, basically this workflow will be production ready.
Okay. Now, an interesting question. You softened.
Yeah, I just wanted to be super clear about for like this cool functionality, that stuff that. Oh, hello. For this cool functionality, that stuff that's under this very thin veil right now, and in the next hopefully few months, that'll be something that you don't have to go through this rigmarole for. But if you're doing stuff that's not, you know, crazy and kind of, you know, stuff like this, you can run one ligand through Sage. You can run 1 million ligands through Sage. That stuff is all good to go right now.
Okay, thanks. So the interesting one is you changed the entire force field to soften all the van der Waals interactions everywhere. With your toolkit, could you go in saying, like, make the ligand, and then could you go into the interchange object and change just those van der Waals that are in the vicinity of the ligand?
Yes, it would take a few more lines of code, so I didn't do that. And I found this was like the more code golfy way to do it, but you could equally well go into the interchange and just scale all the van der Waals there.
Okay, then you could make those, you could locally perturb the force field in the vicinity of the region of interest. That's actually quite nice.
Yeah,
Thanks.
you could look at some characteristic of where that specific ligand atom is and change its parameters according to your own logic.
So thank you, nice demonstration.
Thanks.
Question at the very beginning when you read in this PDB. So I assume as it comes from OpenFold, it has hydrogen coordinates. But where do I worry about the protonation state, tautomeric state of the histidines?
Yeah, so in this case, we do not take responsibility for your protonation state. We won't read a protein that doesn't have explicit hydrogens that has to be provided outside. And there are good tools for that. We ran a workshop recently that used ProPKA to assign those a smarter way.
Yeah, but can I rely on OpenFold to give me the right protonation state?
Jennifer, do you want to? Jennifer, shake your head. OpenFold doesn't concern itself with protonation state. And so I want to give you the honest answer, and the honest answer is it's sort of, it's a very complicated thing, and I'm pretty sure that Open for Energy is going to tell you about how important it is to get the correct protonation state to get the correct answer. And it's a huge question that we don't want to own.
And another comment, as your sanity check, you plotted energies for after the export too.
Yes.
Wouldn't be the more careful check to look at forces? Because this is what we really need in MD.
Yeah, so that would be the ultimate careful check. In this case, you know, we infer that it is unlikely that we get the energies right but the forces wrong, but this is why, you know, so much of this is hidden behind the experimental hill. It does require sanity checking. And if people do try this stuff and they find weird outputs, we commit to fixing them. So please report those.
I can try without mic. I mean, you had your little function that adds harmonic restraints to a point of vector. What would be your recommended way to add more complicated restraint sets? I mean, there's Amber syntax or similar ones which are quite powerful and often quite necessary for MD simulations.
Oh yeah, man, I golfed this so much to make it like, it was already like a big demo, right? No, you could do bonker stuff. So, in the same way that we, pull up what he's talking about. Yeah, this stuff. The restraint edition. So this is all an OpenFold, and here I tried to find the minimum line of code way that I could get the logic to just happen and give me the right output. If you wanted to be more sophisticated, we have topology.toMDTrad and I think 2MDAnalysis methods, where it's really easy to get an OpenFF topology in either of those. And then you get to use their entire selection language, unlike always with our DKit. And we guarantee in those that the add order remains constant. So, it's not like, oh geez, it's going to rearrange my, the index over here, the index over there from doing this search aren't going to match up. We guarantee consistency in add ordering. And so, if I wanted to write more code here and confuse a whole audience, we could have dumped out to our DKit and done a substructure search to decide how to make these restraints, or any number of other ways.
I had a question about the kind of the iterative procedure you had where you mutated the ligand. It wasn't clear to me whether the protein itself changed conformation, whether the pocket opened up. Did you see that happening? I didn't.
Yeah, the protein does change conformation because in addition to just doing an energy minimization, I do 1,000 steps of molecular dynamics. Because in energy minimization will usually leave you kind of on the slope of the potential energy surface. And so I do some MD to relax everything and get down closer to a well. So that's why you may have seen...
Yeah, so did you have like a before and after? Because I don't think I caught like a before and after of the protein itself.
Can you say that once more?
I thought there would be like a visualization of the kind of the initial state of the protein and then the final state where the pocket opened up.
Oh yeah, and so the best I could do, I managed my time poorly. And so all the files will be available to you if you want to take a closer look. But yeah, so starting here, this surface is going to be redrawn every frame in the simulation. So here, this is that first minimized thing, and you see that this surface is bulging in. It's kind of dim. But if you see this kind of...
Yeah, no, I see it.
Yeah, so it's moving in each step, and also the outside protein surface is changing because I'm forcing it to do molecular dynamics, and I just am too lazy to constrain the far outside chains. So the overall surface is changing. Does that answer your question?
Yeah, no, thank you. That's cool.
Yeah, it's fine. And this is, you can feel free to reuse this code. It is what it is, and it's highly golfed to make a good demo. It's more of an example of all the cool stuff you could make by just using this Lego set, more so than an endorsement of using this specific code.
Thank you. Very nice demo. So I basically want to know how much freedom do we have as a user. So for instance, so you just show minimization, right? But then we know that there are two ways to do minimization. Like there's steepest descent and there's conjugate gradient, and then there are we can set the steps of how much we want each minimization. The water model, you're using TIP3P. Can we use any other water model? And so for instance, if we have Gaussian in-house, can we use RESP? I know it would not be ideal to use RESP for 1,000 ligands, but let's say I want to do it for 3 or 4, and I want to use RESP. So do we have freedom?
Yeah, so I think you asked two questions. One is, do I have to use TIP3P? And the other one is, could I use RESP charges? And the answer to both are yes. We provide some alternative water models than TIP3P. We know that TIP3P has huge problems. We're planning on not using TIP3P in a future release. But the thing is that we're co-optimizing our parameters with TIP3P. But we know that it's not the best, but part of our force field fitting is that we try to get the densities of bulk mixtures correct. And if it's a bulk mixture involving water, then we're co-optimizing our small molecule parameters if we have ethanol and water. We optimize the ethanol parameters to get the right density in conjunction with TIP3P. So counterintuitively, and we've never benchmarked this thoroughly, giving a better water model might give you worse results with our force fields because we're co-optimized to TIP3P.
Okay.
The second question is, can you use RESP charges? Yes. You can just take in charges from an SDF, and you can use the charge from molecules argument when you make when you create an interchange, and that will skip doing AOM and BCC charge calculation, and it will just use the exact charge
Okay, and can you also elaborate on how you are running minimization?
Oh, yeah, no, it's just garbage manipulation. I mean, it's stupid percent. There's better engines out there. I mean, this is all OpenMM's territory. And so I'm just doing the minimum I can to have a demo.
I see. Okay, thank you.
The rest of the questions that you might have, you can ask Jeff at the panel. Let's give it up for Jeff once more. Next, we have Hannah from Open Free Energy, who's going to walk us through Open Free Energy.
Okay, cool. Does the mic work? More or less? Okay, perfect. Yeah, so now that we saw how to fold our beautiful MCL1 protein using OpenFold and then parameterize it and the ligands with open force field, I now will take all of that and show you how to run a network of relative binding free energy calculations in OpenMM step by step, so that hopefully at the end you feel comfortable to try it out yourself. And this is also like a notebook that you can run afterwards yourself. But Irfan was so kind to make this beautiful presentation out of it. But yeah, it's also a notebook like the other ones that we will provide for you. And specifically, I will go over a few different steps that it takes you to really, starting from the protein and the ligands, to run the relative binding free energy calculation. We will look at loading and defining our systems. We will then look at how to create these atom mappings and our ligand networks. We will then run the calculations, though that will be kind of like a cooking show experience, because, you know, that's kind of expensive. Then we will analyze our cooked results, and I will show most of this in the Python API, so to get you kind of like the deep dive into how the modularity of our tool looks like, but also we'll show you the command line interface. That's a very good way of using our tools as well. So this is our system, MCL1, as you have heard already, and we are looking at these fragments that you also already saw in Jeff's talk. And so we will focus on these 14 fragments from a screen by Freeberg et al., and they have also been used by actually Thomas, who's in the room in a study back in 2015. Yes, and these are this is like the core of these ligands. And so starting off, we just want to also look at these ligands a little bit closer in 2D. We use our dkit, loading in our SD file that's called ligands.sdf. And this is the overview of the 14 molecules. Again, like the cores are sometimes a little bit flipped, so don't get confused by that. But yeah, we have this carboxylate and then this bicycle with different substituents, and also here sometimes a sulfur or oxygen or nitrogen. So these are the ligands that we will be looking at in this study. We have now our workflow that takes in our inputs, our prepped ligands that are already in the binding pocket, the protein from OpenFold, and wiggled around by open force field. And we will be walking through all these steps. And just to show you kind of an overview, like each step uses different external tools as well. So building on our dkit, OpenMM, LowMap, a lot of different things. Of course, open force field. Yes. In OpenFE, we need a way of how to define our molecular systems. And the way how we define them, we call them components. And we have different components for different parts of our systems. We have solvent components, which will have the water and the ions. We have protein components, and they could be a protein, could also be another biopolymer. And we have small molecule components that, like the name says, that's small molecules, it could be our ligands, but also if your system has cofactors, you would also load them in as a small molecule component. And so here, this is where you can see we define our protein, starting from this protein.pdb. We have our solvent. Here we use an ionic strength of 150 millimolar, and we load in our 14 ligands kind of as a list into our small molecule components. And again, if you had a cofactor, you would also load that in at this point. Now that we have our components, we can go to the next step. We have to map our ligands on top of each other for our relative binding free energy calculations. Here we have two different ligand atom mappers. We have the low-map atom mapper and we have the cartograph atom mapper. Ifan already talked about this in his talk. Low-map is based on like the 2D maximum common substructure between the ligands, while cartograph is like 3D first algorithm. And so in this demo, we will be showing you how to use cartograph, but we also have tutorials for you on how to use the low-map atom mapper. So here we are taking in this case, just the first two ligands, and you can look, we create the atom mapping, and you can look at the atom mapping in 2D. Here in this depiction, the atoms that are not color-coded at all, those are the ones that will be mapped on top of each other, so they will only have a single coordinate in the hybrid topology. While the atoms that are in blue, those are the ones that undergo an element change during the transformation, and the atoms in red, those will become dummy atoms in the respective end states. And so this is a way of how you can access and understand the atom mapping. You can also do that actually in 3D, if you like 3D better. So this is like a nice visualization. In the middle, you can see the two ligands, how they overlap. Is that big enough? I think maybe. So this is just a 3D overlay of the two ligands. Here we have on the left-hand side ligand A, and on the right-hand side ligand B of this one transformation that we're here looking, or this one ligand pair. And here in this case, all the atoms that have a sphere, those are the ones that are being mapped on top of each other, and the same color means those atoms are being mapped, so this magenta atom is mapped on top of this magenta atom. And the atoms that don't have a sphere, those are the ones that will become dummy atoms. Now we don't just want to map, those two ligands. That was just an example for you to see how we can look at these kind of atom mappings. We have 14 fragments, and we want to create a ligand network to compute the relative binding free energy calculations of this network of transformations. And in OpenFE, we have different networks. We have a low-map network that has redundant edges. We have a minimal spanning network. We have radial networks, and also if you, for example, an external network, like from FEP+, you can also load that into OpenFE, or if you want to like hand make your network, you can also load that in. And Ben in our group is working on Connector, a package that will have even more flexibility and different network types. And these networks, we have different functions that all are called generate low-map network, generate minimal spanning networks. And to create these ligand networks, we of course need the ligands. We need a scorer, and here we have the low-map score that basically is a measure of how easy the transformation will be. And then it takes in the mapper, and as I mentioned, in this case, we're using the cartograph atom mapper. And now we have our ligand networks here. We have our network that's built from the MST, so the minimal spanning tree, and those have the mappings included. So again, you can here choose just looking at the first edge in your ligand network and looking at the mapping. So this is how you can also just visualize your mappings in 2D from the entire network. You can either loop over it or just specify, oh, I want to look at the first edge, and here again you can see how we are undergoing this element change of these atoms. You can also visualize in 2D the entire network. So these would be our low map networks, where you can see there are some redundancies, some closed ligand cycles. And on the other hand, in our MST network, we just have single connections. So this is like a minimal network, similar to the radial network. And in this demo, actually, we will stick with the MST network for now. Okay, so our goal is to run relative binding free energy calculations, and for that we use a thermodynamic cycle, where we transform the ligands, like go from one ligand to the other, mutating the atoms that are different, and we do this both in the complex and also in the solvent. So we have to define our end states, like these end states of the thermodynamic cycle. And that's 4 of them. We have 2 end states in the solvent and 2 in the binding site. We have to define our end states, and then we have to define how we want to run the transformation, so the protocol that we want to apply to the transformations. Okay, let's start off with getting our end states ready to go. We define these end states as what we call chemical systems. So chemical systems are just made out of our individual components that are put together to create the end states that we are interested in. For example, in the binding side, you would need the solvent, you need the protein, and you need the ligand. Now, again, we will zoom into just a single edge. Later on, I will show you how to do it for the entire network. But when we just look at a single edge, we take, again, our first edge from our MST network. For this one edge, for this one transformation between the 2 ligands, we have to define 4 different chemical systems, one for the complex, one for the solvent, and that for both of the ligands. And we do this by creating a dictionary of all the components that we need for this end state. So in the complex, like I said, we need the ligand, the protein, and the solvent. While in the solvent, we of course only need the ligand and the solvent. Again, if your system would have a cofactor, here you would want to add that component of your cofactor into the dictionary. Or if you have multiple cofactors, you can also add them simply here into the dictionary. Now, it's kind of an interesting way of thinking about end states, about these chemical systems. We can actually use now these chemical systems to see if end states are the same, then the chemical systems should be the same, or if the end states are different, and then we have to run a transformation to go from one end state to the other one. So here, for example, we can use this method. We can just define another complex. We take a ligand, we take the ligand A, we take the protein and the solvent, and now if we compare this to our ligand A complex, this should be equivalent, because it's the exact same chemical system. If we compare it ligand A complex to ligand B complex, this is not the same, so it returns false, because the 2 small molecules are different. Now we have defined our end states of our thermodynamic cycle. What we now need are like the little arrows that actually connect our end states, and we do this through a protocol. And we gave it in OpenFE this beautiful name. Our protocol is the Relative Hybrid Topology Protocol. You know, it is a very creative name, and this is based on a hybrid topology approach, like the name says, and you can choose different samplers. You can use Hamiltonian replica exchange. We have a SAM sampler, or you can just run independent windows here, and our simulation engine here is OpenMM. Protocols, of course, need settings. You have to define how you actually want to run your protocol, how many lambda windows, how long you want to run the simulations, what force fields to use, and these settings are stored in our Relative Hybrid Topology Protocol .default settings. So you can load all our default settings. You can look at them by printing the settings. I'm not doing that here, but these default settings then also allow you to change them. So you can look at what the default setting is, and if you don't like it, you can change it. For example, here we want to look at our force field settings, and more specifically in our small molecule force field. Oops, I think I didn't run. Last line is, oh yes, I came in there. Ah. Perfect. So our default force field setting is the OpenFF 2.1.1, but then Jeff gives us a call and says, you know, we got a new force field. And so of course we want to try it out, and so we change the default here to the new OpenFF 2.2 and run the simulation. That you can also, like I said, change the length of the simulation, the number of lambda windows, a lot of different settings to customize your workflow depending on the needs for your specific system. Now we have defined our settings. We are confident that those are the ones that we want to use, and we feed them back into our relative hybrid topology protocol. And this protocol itself then takes the settings and becomes immutable. And this protocol we can then reuse within our network for all our different transformations. Okay, so now going back, thinking about the thermodynamic cycle, we have defined our different end states, so our chemical systems. We have defined the errors between the end states, which is our relative hybrid topology protocol. And now we want to create transformations. And the transformations really just combine all of the above, all of what we have done so far. So they take in our end states, the two chemical systems. They take in the atom mapping that defines how we want to actually mutate the two ligands into each other, and it takes in the protocol, and the protocol itself has all the relevant settings. You can also give it a name, you know, if you want to not confuse your file names, or if you want to know at the end, you know, what you actually simulated. And so this is what we're doing here. We need a transformation for both legs in our thermodynamic cycle. So for the complex, which takes in the chemical systems that define the end states in our complex, and then the same for the solvent here. Okay. Oops. And these transformations then you can save to disk in JSON format to run them later. Now, so far, we just looked at a single edge kind of to go into a deep dive of all the different things we need. But of course, we have our MST network. We want to simulate all our 14 ligands and all the transformations between these ligands, so we can conveniently do this all together and create a whole alchemical network that consists of all the alchemical transformations that we need to run this network. And the way how we do is that we just loop over all the edges in our network, and over the two legs in our thermodynamic cycle, we create the chemical components, and we create the alchemical transformations from the chemical systems, from the mapping and the protocol that we're applying. Very fast. So for this, we don't actually need a cooking show. This is all very fast. And now we can, again, store all these transformations to disk. And I forgot to import something. I think I forgot to run some. Okay. This is actually my first live demo ever, so I hope that it doesn't become a disaster like the RDKit one, but you know, we will see at the end. Yes, so we can save all the transformations to disk, which hopefully now works, and you can see that we saved them, all the ones for the complex phase of our thermodynamic cycle and for the solvent as well. Okay, so this was a lot of lines of code. Of course, like, we have tutorials for this. You don't have to memorize all of this. We will provide this. But another way of just very easily get to this point is using our command line interface, and this would actually, all the above is summarized in a single command line. In addition to just using our default options, you can also customize your settings in the command line by providing a YAML file, like a settings.yaml, for example. And here in this case, we want to define that we use the atom mapper cartograph just to do the exact same thing as in the Python API. And we ran this, or we prepared a minimal spanning network. So this is the network that we will also specify in our YAML file. And this is the command that you would run. It's called plan RBFE network. And like I said, all the steps that you have seen up to this point are summarized in this single command. So it takes in the ligands, it takes in the protein, it takes in the settings YAML file where we said we want to use cartograph and we want to use the minimal spanning tree network. And it creates the same JSON transformation files as from the Python API. So this is a very convenient way as well to set this up. Okay, so now we have done all we need to actually be able to run this entire network. Like I said, this is now the part of the demo that's not live. This is our cooking show where Irfan already prepared and ran this ahead of time so that we can actually look at results today. But how you would do this is using our quick run CLI command, where you just give it the path to your transformation.json file that we saved to disk, or that also came from running that command line command, and you give it the name of how you want to call the results, in what directory you want to store the results in. And this command would execute the simulation for a single transformation, but we have an entire network, so in reality you would, for example, run a for loop over all your transformations and put that in a bash script and run it on your HPC cluster. You could also use Alchemiscale to submit your calculations. We've heard already a little bit about that execution engine. And very shortly, coming in OpenFE will also be Exorcist, is another way to run your simulation on a large scale as well. Okay, so now we're done with our simulations. That was fast. Our whole network finished in seconds. And we want to now analyze the results. Or first of all, actually, we want to look at the results we generated. And these are the files. This is for one of the, if you look at this, for one of our solvent-leg transformation, we are generating a bunch of different files. This is, on the one hand, very structured files. So we have a PDB, we have trajectory files, if you want to really look into that. We also have some automated analysis, both on the structural side, looking at the RMSD and other metrics. And for example, here you can see the EMBA overlap matrix. That really helps you to access whether you can trust your results or not. So you would want to see at least 0.05 overlap here on the tri-diagonal, also on this diagonal and this diagonal. This looks healthy, so we can continue with analyzing these results. And here we also have a CLI command, which is called gather. Makes sense, I think. We look at, we give it the directory where we stored all our results files. And now you have different options. I will first show you this one. Here we want to get the actual delta G of binding of our ligand network. So here you can see all the transformations and the delta G that we obtained. You can also get the actual delta G of the individual ligands, and this is obtained using Cinnabar, which uses a maximum likelihood estimator to go from the delta G to the delta G values. And these, because until right now we haven't given it any experimental data, it just centers all these delta G results around 0. So these values itself are meaningless, but the correlation between the results is what we're interested in. And if you actually do have experimental data, you can also give Cinnabar those, and that you can get these beautiful plots looking at the correlation between our calculations that we just ran and the experimental data points, both here of the delta G and of the delta G. And in this case, I would say this looks very good with a low RMSE, and also here the R-square with 0.67 looks reasonable, and this is actually very comparable to the results from Thomas's study. Yes, and this is it. Like, this is how you can run RBFE calculation in OpenFE. We put this demo on, I believe, on GitHub, or I share it on the Discord as well. And on our documentation homepage, we have also tutorials that do the same thing, like walk you through the process step by step, using our CLI, using our Python interface. We have different cookbooks that kind of take a deeper dive into one of our topics. If you want to, for example, look more into the visualization of atom mappings, or other tools. And yeah, I hope that if you find anything that you don't understand in our documentation, that you just email us. We are always happy to improve upon it. And I'm happy to take any questions.
Yeah, thanks for the nice demo. So I was wondering, if you have the very same ligands but different conformations, so would they be considered also as different to be able to basically run free energies on different docking poses?
Yes, you are, especially with the cartograph atom mapper, since it doesn't look at the 2D similarity, but the 3D, this is definitely possible. One thing is that it would be good to give it different names. I think that's something we notice. If you give it the same name, it still creates the network correctly, but the analysis is then a little bit tricky. But yeah, that's definitely possible to do that. Yeah.
Very nice demo. When you run at scale, do you tend to run all of the lambda windows sequentially, or do you try and parallelize across lambda windows?
So in OpenMM, all the lambda windows are run on a single GPU. And since here we're doing replica exchange, they have to run at the same time, or you always have to wait for one another. And so yeah, that of course can slow things down. Yeah, because we're limited to a single GPU for all the lambda windows. Yeah, that's what we're doing.
Where do you set how the calculations actually run? The refreshing protocol, the number of windows, and length, and are your defaults there reasonable?
Yes, that's a good question. I can just actually, so that we define in our settings. Up. And I will actually just show you, where are we? Here. So these are our settings, and I will just add an additional. So here you can basically see all the, is maybe a little bit overwhelming. It's very small. Let me zoom in a little bit. Oh, there's zoom out. Yes, so different things we can set. For example, different force fields. As I already mentioned, we have here, for example, the number of lambda windows that you can change. Here, the lambda function itself, you can also change. The default that basically does the Coulomb and van der Waals separately to avoid singularity problems. We have different an area where you define your simulation settings. So the number of minimization steps, where you can, here we run every lambda window for 5 nanoseconds, which we could also adapt. We have output settings where per default we are, for example, not storing water molecules in the trajectory just to save disk space. But if you want to analyze also the waters in your system, this is something you would have to change. Our solvent model is TIP3P, and this is basically, I know this is like a very big dictionary of a lot of things. So yeah, but I hope that this helps the expert user to really get into this and being able to change the different settings. And we have these these larger classes. So in the example that I showed you previously, we have the force field settings, so that would be here, and then we have these subclasses like the small molecule force field, and this is how you then adapt the settings away from the defaults. So you start off with the defaults, and then you can define your custom settings in this manner.
That's easy. Yeah, a question. Would it be possible to provide like pre-thermalized conformation, for example, for the complex? Pre-thermalized, so I have a previous long simulation and I want to use that one as an input.
Yes. So you can definitely take the protein from that, and you can take the ligand. Yeah, like you can extract the protein from that and the ligands. The solvation currently we do within our ecosystems. I think if you could also go into the code and I think insert things at a later stage. Am I correct? But that would definitely yeah. So right now we recommend if you run, for example, an MD simulation to pre-equilibrate your protein, then you would just take the last snapshot from that, extract the protein, for example, using MD trash, and then you can give us that protein with the ligands still being in the correct position in the binding site by, for example, aligning them first, to be correct. Yeah.
Is it possible to extend a run? Like, suppose you've decided you want to run it 4 times longer to get better precision.
Unfortunately, currently not. But yes, that's definitely something that we want to change going forward. Yes, but currently, unfortunately, not. Yes, so currently the protocol and the mappings are kind of separate. So they are both ingested by when we create the actual chemical transformation, so that takes in the mapping and the protocol. So definitely at that stage, we have to make sure that whatever we want to do with the mapping and whatever our protocol is, that aligns. But yes, in this talk, I think we structured it like this, that, we do the mapping, then we define the protocol, but those are independent right now.
So I could use the protocol to affect the edge weightings that would be used to determine.
You mean kind of like having the protocol affect the score that you use to create the network? Yes. Yeah, that's an interesting idea. We don't do that right now. I think definitely scores in general is something that we're looking into just improving upon. And yes, I agree that once we go into things like ladybugs, I think the way how we think about this. Yes, we'll. Yes, yeah.
Hi, is there any point in the simulation setup process in which the files can be exported in a way that could potentially be read by a different simulation engine if, for instance, you did not want to run in OpenMM or use like some enhanced sampling method that wasn't supported?
Yes, so different parts can be exported. For example, our components in the very beginning, we have like either like 2 open force field or 2 OpenMM or even 2 PDB file if you want to save the protein back. That's definitely possible. Our mappings, they are actually just, I think as you saw, just can be just a dictionary of indices. So you can hopefully also use them in a completely different software package. So this is, this is a goal. About the actual transformation, this is something Irfan, you would have to, I'm not sure.
I can speak to that. So the
we didn't support that engine, we would then suggest you use as much components that we can give you, and then you maybe use something like interchange to just create a system, write it out in the right form. But yeah, so for example, in the protocol itself, that would be component specific.
Nice presentation. I asked before about protonation states of the protein. Where do I take care?
We need a new consortium, though.
So for this particular thing, I ran protons ahead of time on it, and the protonation state was fine. But the current take is that when you pass in the PDB, it should be in the right protonation state.
Yeah.
It's up to the user to do.
Yes.
As Hannah said.
That it's, yeah, I think it's a big black hole that I feel like would need a whole new project to, yeah, but yeah, so right now our users really have to be the ones to prepare the protein, to model missing loops, to do everything to be MD ready.
Okay, any more questions that you have, you can ask Hannah and Irfan at the panel later on today. Let's give Hannah another round of applause. And now we're going to break for some coffee. Go ahead and enjoy yourselves. We'll reconvene in about 30 minutes.